Good morning. In the past few lectures, we have been studying the phenomena of interference and diffraction. In both of these phenomena, we had light, we had waves of the same frequency and wave number being superposed, and we were interested in studying the spatial intensity variations that arose when we superpose such waves. And these intensity patterns arose because sometimes at certain points the two waves or the various waves that were being superposed were all in the same phase, so they added up to increase the intensity. At some other points the waves were such that the phases of the waves were such that they cancelled out and you had a very low intensity. This gives rise to the pattern of fringes, etc. Now, in today's lecture, we are going to discuss a slightly different situation. We are going to discuss a situation where we have the superposition of two waves of different frequencies. For two waves of different frequencies, we are going to study the variation of the intensity with time. So, let us consider two waves, one of a frequency omega 1 e to the power I omega 1 t and A2 So, we have two waves of two different frequencies. We are interested in studying the time evolution at a fixed point. So, I have not shown the x dependence, but the x dependence is there. They are sinusoidal plane waves. So, the usual x dependence minus kx is going to be there. I have not shown it. The wave numbers are also different. So, we have two waves of different frequencies and we wish to study the superposition of these two waves. So, these are complex. This is the complex notation. So, we have in this situation considered the amplitudes of the two waves to be identical and we have superposed them, and this can be simplified to some extent. So, if we define the mean frequency omega bar to be omega 1 plus omega 2 by 2 delta and the difference to be omega 2 minus omega 1, then we can write omega 1 as delta omega by 2 with a minus sign plus omega bar, and omega 2 is delta omega by 2 plus omega bar. So, with this new notation of omega bar and delta omega, the superposition of these two waves, or let me write down these two waves themselves first. So, the first wave written in terms of these variables, written in this way, the first wave becomes A1 This is the first wave with frequency omega 1, this is the second wave with frequency omega 2. when we superpose these two, we have AT is the sum of these two. So, this part can be taken common. The sum of these two is going to be 2 cos. So, this is going to be 2 cos delta omega by 2 t into e to the power I omega bar t. And we are interested in a situation where omega 1 and omega 2 are very close. If omega 1 and omega 2 are very close, then delta omega, the difference in the frequencies, is much smaller than the average frequency. So, that is the situation we are interested in. We have two very close frequencies, the superposition of two waves of very close frequencies, and the resultant, the superposition of these two looks like this. So, this can be interpreted as follows. We have a fast oscillation at the average frequency of the two waves. The amplitude of this fast oscillation itself oscillates slowly at the difference, at the frequency which is the difference of the two frequencies. So, we see that if we superpose two waves which are very close in frequency, the resultant is a fast oscillation at the mean frequency, and the amplitude of the fast oscillation at the mean frequency itself varies slowly at the difference frequency, the difference at the frequency which is the difference of the two frequencies. This has we can interpret this physically. This is what I am going to do for you now. So, this picture shows you the two waves, and the oscillations of the two waves, they have two slightly different frequencies. So, omega 1 t and omega 2 t, there is a slight difference between these two. To start with, the difference is 0. As t increases, the difference keeps on increasing, and then this difference between omega 1 t and omega 2 t. So, there is a difference between omega 1 t and omega 2 t, and this difference keeps on increasing, and so this this is the difference. This difference keeps on increasing as time evolves, and so the oscillations also differ as time evolves, and the difference again vanishes when this becomes 2 pi. You see so the difference between the two oscillation keeps on increasing, and then again it goes down, and finally the two oscillations again match when the difference between omega 1 t and omega 2 t is 2 pi, and the difference between the two oscillations become exactly opposite when the difference is exactly pi, which is what you see here. So, the two oscillations start out exactly the same, but there is a small difference which keeps on increasing with time, and then this difference, when it becomes pi, the two oscillations are exactly out of phase, which is what you see over here, and then they again become 2 pi, the difference becomes 2 pi, so they are again in phase, and again they will go exactly out of phase again when it becomes 3 pi, and again it will be exactly in phase when it is 4 pi, etc. So, the superposition of these two is going to be the combination of these two is going to add up when you are somewhere in this region, and then it is going to cancel out. The superposition of these two waves is going to cancel out over here, and then again it is going to add up over here. So, what you have is essentially that the two waves are going to add up in these regions, they are going to cancel out in these regions, and again they are going to add up in these regions. So, the fact whether the two waves are going to add up or cancel out is changing slowly, much slower than the individual oscillations, and the fact whether they add up or cancel out, the superposition of the two waves, depends on this difference of the two angular frequencies omega 1 and omega 2, and the resultant looks like this. So, you have the fast oscillation, and the amplitude of the fast oscillation changes, it becomes 0 when the two oscillations are exactly pi out of phase, and then again it adds up when they are 2 pi out of phase, again it becomes 0 when they are 3 pi out of phase, and so forth. So, you have this slow modulation, slow change of the amplitude, which is referred to as a modulation of the amplitude. Now, let us, so this is what happens. Now, let us discuss the situation where, such a situation occurs in many contexts. So, for example, I have two strings which produce nearly the same frequency, but not exactly the same frequency. For example, I am tuning a guitar and I have not exactly tuned it. So, when I pluck the two different strings, they produce very close sounds, but not exactly the same. The question is, what do I hear when I pluck two strings which produce very close frequencies, but not exactly the same frequencies? So, let me go through this repeat this analysis which I had just performed. So, we have now a superposition of two waves of slightly different frequencies. The amplitudes could also be different. So, let me put different amplitudes here, A1, A2, and we are going to superpose these two. And we have gone through this exercise, and I showed you that this could be written in terms of delta omega and omega bar. Now, there will be a factor of A1 here and a factor of A2 here. So, when I superpose these two, let me write down what we expect to get. The superposition of these two is going to give us AT is equal to A1 e to the power minus I delta omega by 2 t plus A 2 e to the power I delta omega by 2 t into e to the power I omega bar t. Now, what we actually measure, what the sound that the ear actually measures is the intensity. So, let me calculate the intensity. The intensity is the time average of the what you measure is the time average actually. So, you see there is let me calculate the intensity, and things will be clear then. So, the intensity is going to be, okay, before going into the question of the intensity, let me just come back to this. Suppose I had exactly the same amplitudes, then this would be the result of the superposition, and the question is now how to calculate the intensity. Now, our ear cannot record when I have a sound wave, the air goes back and forth, that is what happens, and our ear cannot record these individual movements. We do not record these individual movements. Our ear drum goes back and forth at the high speed at which the sound wave is making it oscillate, but what we record is the time average intensity. For example, if I have a sound wave, a sound at 500 hertz, the ear drum goes back and forth every 500 seconds. What we record is the time average intensity. So, the time average that we record is over a much larger, is this intensity, is the average intensity averaged over a sufficiently large time, so that there are many oscillations in between. Now, suppose I have a situation where I have one sound at 500 hertz and another sound at 501 hertz, we have the superposition of these two is a fast vibration, is a fast oscillation. The fast oscillation is going to be at the average omega bar, which is 500.5 hertz, and the amplitude of this fast oscillation is going to get modulated at delta omega, which is the difference which is the delta omega is 1 hertz, and the amplitude is going to get modulated at 0.5 hertz. Now, the point which we should recognize here is that we will not experience. So, when we experience this sound, we will not experience these very fast variations at 500 hertz. What we don't 500.5 hertz. What we record is the time average of this, but we will experience this variation at 1 hertz. This we will at 0.5 hertz. So, this will be experienced. So, the point to note here is that the ear does a time average on a time scale which is intermediate, somewhere in between this and this. So, this thing gets averaged out, but this part does not. We can record this variation because it will have a time period of the order of a second, and our ear can record this variation. So, if you ask the question, what is it that we are going to hear, we should take the time, consider the time average over this variation, but not over this variation. So, this is where we have to take a look at the instrument which is doing the measurement and apply the suitable time average. So, let me do this in the fully real notation here. So, the way to calculate the intensity is to take the quantity that you really measure is the real quantity, is the real part of this expression. The real part of this expression is AT, which is 2 cos delta omega by 2 t into cos omega bar t. This is the actual physical vibration, and to calculate the intensity I have to square this and put a factor of half, and take the time average. This gives us half, a factor of 4 here, which is an overall normalization anyway, not of great interest, and then I have cos square Now, over here the intensity that we are going to record with our ear is going to be the time average. So, the question is this is the time average of this. The question is, should we average the product of this, or over what time scale are we averaging? So, as we have already discussed, we should average over a time scale which is intermediate between this and this, so that this gets averaged out, but this will not get averaged out, and this time average is going to give us 2. This is going to still remain cos square delta omega by 2 t. This time average is going to give us a factor of half. We are not going to be able to record the fast variation over here. So, what we will record, what we are going to experience is the slow modulation, the slow change in the amplitude, because that is going to occur on the order of a second, and this cos square delta omega by 2 t can be written as with the factor of 2 outside, can be written as, we know that cos square x is 1 minus cos 2x. So, we can write it in terms of cos 2x, and you see that you will essentially hear a modulation in the intensity at an angular frequency corresponding to the difference, and this will occur at, so this is going to occur at the time scale of 1 hertz, which our ear can make out. So, that is the point which I was trying to make here. So, let me go back to the calculation which we were doing. So, we have the superposition, we have this kind of a wave which is a product of a slow variation here and a fast variation over here. And the question is that what is going to be the intensity. So, time average, the intensity is the time average of the square of this with a factor of half, which I can write in this fashion. And we should remember to do an average over all time scales, which are over a time scale which is somewhere intermediate between this and this. So, if you take the complex conjugate of this time average, this complex conjugate of this, what you get is this into e to the power minus I omega bar t, and we multiply these two. So, these two factors will cancel out, and this into this is going to give us a1 square, this into this is going to give us a2 square, half of that factor of half. So, this is going to be the intensity of the first wave plus the intensity of the second wave plus, so the intensity is going to be half a1 square plus a2 squared, the product of this and this is going to give us, there is going to be a a1 square plus a2 square, and then we are going to have the cross terms. The cross terms are going to give me a factor 2 a1 a2 cos omega 2 minus omega 1 t. So, what we see is that the intensity of the superposition of these two waves is going to vary slowly with the difference in the two frequencies. So, the intensity is going to have a slow variation with the difference of the two frequencies, and if a1 and a2 are exactly same, the intensity is going to have a maximum value which is 4a square, 4 times the individual intensity, the minimum value is going to be 0. If a1 and a2 are not identical, then the variation is not going to go between 0 and the maximum value, it will have a minimum and maximum value, the minimum being more than 0 and the maximum being less than what you have in this particular case. So, this is the phenomena of beats. So, what you will hear if I play two strings which are whose frequencies are very close but not exactly the same, the intensity is going to go up and down slowly. It is as if someone were slowly turning the volume knob, it is going to go up and down slowly and it will be a discernible. The closer the frequencies get, the slower is going to be the variation, and finally the variation is going to stop when the two frequencies are exactly the same. It is going to get a very large time period, you are going to have a very large time period variation, which is what I have shown you over here also. The amplitude essentially goes up and down slowly, and the time period of this variation of the amplitude is inversely proportional to the difference in the frequencies that you have, and this is also referred to as the modulation of the amplitude. So, this was the phenomena of beats. Now, let me go on to a different application of this discussion. This has to do with amplitude modulation and how signals are transmitted. So, let us ask the question, how are signals transmitted in using radio waves? We all must have seen radio receivers and transmitters. The question is, how does this work? We have already discussed one aspect of how it works, how the antennas, we have already discussed that there will be antennas. If you give an oscillating signal to the antenna, it emits radiation, and then you have other antennas which, when there is a radiation incident on it, will produce an oscillating signal. But now we ask the question, how do you use this whole thing to transmit a signal? So, let us discuss that. So, the way the whole thing works is as follows. In the radio station where the signal is being transmitted, you have a signal generator which produces what is called a carrier wave. So, this produces what is called a carrier wave. So, let us consider a situation where the carrier wave has, for let us say 800 is at 800 kilohertz frequency. So, the signal generator over here, this is going to be referred to as omega c. The signal generator over here produces a wave at 800 kilohertz. It's a wave like this, a sinusoidal wave like this. This itself has no information. Now, I would like to use this wave to carry the voice signal. So, let us just say that I would like to somehow encode my speech, the voice, my voice onto this radio wave. So, my voice spans the frequency range from, let us say, 20 hertz to 20 kilohertz in sound waves. So, by using a microphone, my voice could be converted into a electrical signal, and what is done is that, so this is my voice comes in over here, this is my voice, the signal which we wish to transmit, and this is the carrier wave, and the amplitude of the carrier wave is modulated so that the changes in the amplitude are the signal which I wish to send, which is what I have shown over here. So, this is what is called amplitude modulation. So, the amplitude of the wave, of the carrier wave is modulated, it is changed so that it has my voice signal. So, let me explain this pictorially. Suppose my voice signal looks something like this. So, I will now change the amplitude. To start with, the amplitude of this signal is a constant. I will now change the amplitude of this signal so that it now looks like this, and you have this. So, the carrier wave is still over here. So, the amplitude of the carrier wave is changed by means of some electrical devices. The voice which I wish to transmit, is the amplitude of this carrier signal is modulated so that it has the signal which I wish to transmit, and mathematically we can express it like this: Ft is the signal that we wish to transmit, and the 1 plus Ft is the amplitude of the signal that is coming out, and this signal is now fed into the antenna which transmitted. So, the signal generator produces a signal at the carrier frequency, the amplitude of this is then modulated with the signal that we wish to transmit, and this is what is transmitted. At the receiver end, again there are devices through which only the changes in the amplitude are recovered, and from this you can get back the voice which you wish to transmit. So, this is what is called amplitude modulation, and this is shown over here pictorially. So, this is the carrier signal, it oscillates at the carrier frequency, and this is the signal which you wish to transmit. So, the signal that you wish to transmit is encoded, it is put in to the modulation of the amplitude. So, the amplitude of this signal is made to change as per the signal which you wish to transmit. This is why it is called amplitude modulation. It is the modulations in the amplitude that carry the signal that you wish to transmit. Now, let us consider an example of amplitude modulation. So, we will consider a specific situation where the signal that we wish to transmit. So, this is the signal that we wish to transmit. We will consider a specific situation where the signal that we wish to transmit is a pure cosine, a sinusoidal wave of a single frequency called omega m, the modulation frequency. and it has an amplitude AM. So, this is the signal that we wish to transmit. So, this is the signal that is modulated onto the amplitude. So, the amplitude modulations in this case are sinusoidal oscillations at a different frequency, the modulation frequency. And we are going to assume that the modulation frequency is much smaller than the carrier frequency. So now we are going to consider a specific situation where the signal that is being modulated, the modulation is itself a pure sinusoidal at an angular frequency omega m, the modulation frequency, and it has an amplitude AM. So, in such a situation, the total signal that comes out of the radio transmitter can be written like this. So, the carrier frequency is still there, e to the power I omega c t, but you have these two extra terms, and the two extra terms are at two different frequencies, and they occur at the frequency omega c plus the modulation frequency and omega c minus the modulation frequency. Now, if you ask the question, what is the frequency content of the signal that is actually transmitted? So, this signal that comes out over here is now said to your antenna. This is your antenna, there will be some tower on which the antenna is placed. So, the question, so let me go through the steps again. You have a signal generator that produces the carrier frequency, which in this case is 800 kilohertz. The amplitude of the carrier frequency is modulated. In this case, the modulation itself is again another sinusoidal at omega m, and we ask so the amplitude of it is modulated, and this is now fed to the transmitter, and the question being asked is, what are the frequencies which are present in the signal that is transmitted? And we have done the exercise over here, and we find that there are two new frequencies that have come in. So, if you send the signal that comes out into a spectrometer, you will find that there are three different frequencies which are present. The carrier frequency is present, no doubt, but there are two new frequencies. One is the carrier frequency plus the modulation frequency, and another is the carrier frequency minus the modulation frequency. So, there are two new frequencies that are present. So, what we have seen over here is something very important. What we have done is that we have modulated the amplitude of the carrier wave, and the modulation itself is a pure sinusoidal of a fixed frequency, the modulation frequency. And we see that as a consequence of this modulation, we introduce two new frequencies. These two new frequencies that we introduce are called sidebands. So, there are two sidebands which have been produced, one at the sum of the carrier and the modulation frequency, one at the difference of the carrier and the modulation frequency. Now, here we have considered a specific kind of modulation which is at a single frequency. Now, if we modulate my voice, for example, onto the carrier frequency, my voice spans the entire frequency range from 20 hertz to 20 kilohertz. So, what is going to happen when you modulate this 800 kilohertz carrier wave with my voice? The difference that is going to occur is as follows. Instead of producing sidebands which are at single frequencies, you are not going to produce sidebands which will look like this on both sides. You will have two bands, and the band, so this is the omega carrier, and this is going to span, or if I work in terms of nu carrier, the carrier frequency is nu c. The sidebands are going to be from nu c minus 20 hertz to nu c minus 20 kilohertz on one side, and so this band over here is going to span from the carrier frequency minus 20 hertz to the carrier frequency minus 20 kilohertz. My voice spans this entire frequency range. So, the sideband is also going to have the same bandwidth as my voice. You are also going to produce another sideband over here, which is going to span from the carrier frequency plus 20 hertz to the carrier frequency plus 20 kilohertz. Okay, so you are going to produce, so every radio transmitter is going to operate, if you are going to modulate the signal, if you are going to modulate the amplitude of the carrier wave with the signal, every radio transmitter is going to actually send out signals not at the carrier frequency, but in a band of frequencies around the carrier frequency. Typically, the high frequency parts are not recorded, they are not very crucial unless you really want to have a high fidelity transmission, and typically the bandwidth the voice is recorded over is 10 kilohertz, not 20. So, typically each transmitter will span nu c, the carrier frequency plus minus 10 kilohertz. So, let us consider a few implications of this. So, in this particular case, the entire voice signal will be distributed from 790 kilohertz to 810 kilohertz. Now, consider a receiver. So, this is the transmission. Now, consider a receiver which is tuned at 800 kilohertz, but which is tuned to a very narrow bandwidth. Let me just tell you how the receiver is tuned. Receivers are tuned using an LCR circuit. So, the antenna will be coupled to a LCR circuit. The LCR circuit has a resonance decided by the values of L, C and R. So, by changing the capacitance, usually the value of the capacitance is connected to a knob, the capacitor will be connected to a knob. So, if you rotate the knob, the capacitance will change, and by changing the capacitance you can change the angular frequency, the frequency corresponding to the resonance, and so it will be tuned to a different frequency. Now, suppose the resistance is, the width of the resonance is decided by the value of the resistance. If the resistance is 0, then you will have a very sharp resonance, basically of no width, but there is always going to be a resistance. So, if you have a finite resistance, there is going to be a finite width, but if the resistance is very small, the width is going to be very small. So, suppose my resonance is so narrow that my receiver is tuned from the frequency range 801 between the frequency range 799 to 801 kilohertz only. Or let us say even smaller, so 899.9 to 800.1. So, suppose I tune my receiver is such that it is tuned at 800 kilohertz, but it can receive frequencies, it is going to be sensitive to frequencies only in this very narrow range of frequencies around this frequency. Question is, can you reconstruct my voice from the radio signal only in this very narrow range of frequencies? No, because my voice spans the entire frequency range of 10 kilohertz. So, you have to, your radio receiver also has to be sensitive to the entire band, to the entire sideband, to one of the entire sidebands, to be able to receive, to be able to reconstruct my voice from the signal that is being transmitted. So, the receiver itself has to also receive the entire sideband. Both these sidebands contain the full voice signal. So, as long as the radio receiver can receive one entire sideband, it can reconstruct. So, you will be able to hear what I am saying, but if it cannot receive the full thing, it only receives a part of it, you will not be able to make out what I am saying. Maybe the high frequency parts will be missing in the radio, in what you receive, what you hear in your radio receiver. Consider another situation where I have one transmitter working at 800 kilohertz, another transmitter working at 790 kilohertz. Now, the sidebands of these two transmitters are going to overlap, and what you receive, what you are going to receive then is going to be some kind of a junk. So, it has to, one has to ensure that the radio transmissions occur sufficiently far apart in frequency, so that the sidebands that are produced do not overlap. And typically the whole frequency range from 500 kilohertz to 1500 kilohertz is available for amplitude modulation AM transmission, and you can fit in a large number of radio stations in this entire range of frequencies. So, until now we have been discussing the behavior of the superposition of two different frequencies at a fixed position only as a function of time. Let us now discuss the full space-time behavior of the superposition of two different frequencies. So, this is what is shown over here. We have two waves of two different angular frequencies, omega 1 and omega 2. We are also interested in the spatial evolution of these waves. So, the wave numbers are also different, and we have written down the full space time evolution now. So, we have e to the power I omega 1 t minus k 1 x, and here we have omega 2 and k 2 instead of omega 1 and k 1. Now, we can repeat exactly the same exercise which we had done when we had looked at the time evolution. So, we could write omega 1 and omega 2 in terms of the mean angular frequency and the difference in angular frequencies. We can do exactly the same thing with the wave numbers also. So, we could also introduce the average wave number and the difference in wave numbers, and the superposition of this is we have already worked it out. If you superpose these, when we looked at it as a function of time alone, we had got this cosine into e to the power I omega of the average angular frequency. So, now when I keep the spatial dependence, what we get is again a cosine. Now, we have delta omega by 2 t, which we had earlier, but we also have an extra term minus delta k by 2 x, which incorporates the spatial dependence, and similarly we have minus I k bar x over here. So, it is just a small generalization of the exercise which we have already done in the beginning of today's lecture, just that we have now incorporated the spatial dependence also. So, now you see that it is this, the resultant is a product of two different functions of space and time. This is a fast varying function of space time, both of space and time. So, this is a faster varying function compared to this of space also, because k bar, the average wave number, is much larger than the difference in the wave numbers. So, we are assuming that delta omega and delta k are small compared to omega bar and k bar respectively. So, this function varies rapidly in space and rapidly in time. The amplitude of this wave varies slowly in space and slowly in time. Now, so when we superpose two waves of two slightly different frequencies, what we get is a fast travelling wave again at the average frequency, but the amplitude of this wave gets modulated, and it again itself behaves like a wave which propagates, which has a small wave number and a small angular frequency. So, the modulation of the amplitude is represented through this. Now, let us ask the question, at what speed does the amplitude of the modulation of the wave propagate? The wave itself propagates at the phase velocity, which in this case, so when we say that the wave itself propagates at the phase velocity, the fast part propagates at the phase velocity, which is omega bar by k bar, and the modulation of the amplitude itself propagates. You can determine at what speed the modulation propagates. The modulation will propagate at the speed delta omega by delta k, and if you take delta omega and delta k going if you take the limit where the difference in the two frequencies goes to 0, then you get the speed at which the modulation propagates, that is called the group velocity, which is d omega by dk. And we have already discussed that the modulations can be used to send information. So, the group velocity usually tells us the speed at which information can be carried by the wave. So, it is the propagation of this modulation that carries information, that carries signal, and the modulation in the amplitude itself propagates, as you can see here, at a speed which is the ratio of this delta omega to this delta k, the ratio of this coefficient to this coefficient. And this ratio is called the group velocity d omega dk, and this tells us the speed at which the modulation propagates, and this is usually the speed at which you can send signals using the wave. So, this is called the group velocity. So, let me summarize this. The phase velocity tells us the speed at which the phase propagates, but this itself carries no information, no signal. To send a signal, you have to modulate the amplitude, and the modulations in the amplitude, they propagate at the group velocity, which is d omega dk, not the ratio omega by k, but at the group velocity, which is d omega by dk. So, the modulations propagate at the group velocity, and usually the signals also propagate at the group velocity d omega dk, usually, not always. Let me consider an example. The example is as follows. The refractive index for X-rays in materials is known to be less than unity, and it is given by the expression over here. So, the refractive index for X-ray in materials is found to be of the form 1 minus a constant divided by omega square, where the constant A is positive. So, the refractive index for X-rays inside materials is less than 1. Now, you must have heard that inside medium light, the refractive index, that is the speed of light, changes inside medium, and the speed of light inside the medium is given by its refractive index, and usually the refractive index is more than 1, and the speed of light is c divided by the refractive index, which is less than 1, less than the speed of light in vacuum. But for X-rays you have a different situation. The refractive index is less than 1. So, the speed of light inside medium, the speed of X-ray, the phase velocity to be precise for X-ray inside medium is also more than the speed of light in vacuum. So, the problem which we have been given, the problem over here is to calculate the phase velocity and the group velocity for X-rays inside the material. So, the phase velocity, we will use Cs to denote the phase. Let us use Cs to denote the phase velocity. The phase velocity is the speed of light in vacuum divided by the refractive index, which in this case is c divided by 1 minus a by omega square. So, that is the phase velocity inside for X-ray inside the medium, which is more than the speed of light in vacuum. Now, the phase velocity we know is the ratio of the angular frequency to the wave number. So, this is equal to c divided by 1 minus a by omega square. Now, we want to next calculate the group velocity. To calculate the group velocity, we have to calculate the derivative of the angular frequency with respect to the wave number. So, what we do is we obtain an expression for k in terms of omega. Let us do that. So, k is going to be omega 1 by c 1 by c into omega times this expression over here. So, we have one term which is omega by c, and then we have another term which is going to be minus. So, the factor of a will come on top, a by c omega, right. So, that is the value of the wave number in terms of the angular frequency, and we can use this to calculate dk d omega. So, let us differentiate the expression for k with respect to omega. Dk d omega is equal to 1 by c minus a by c. Now, if I differentiate this with respect to omega, I will get plus 1 by omega square, which gives us d omega by dk is equal to c divided by 1 plus a by omega square. Okay, so the group velocity we see is more than is less than the speed of light in vacuum. So, let me just explain to you the significance of what we have done. For X-rays in materials, the refractive index is less than 1. It implies that the phase velocity of X-ray in a material in materials is more than the speed of light in vacuum. But as we have already discussed, the phase velocity is not the speed at which you can send signals using the light. So, if you use your X-ray to send a signal, the modulations, you will have to modulate the wave, and the modulations travel at the group velocity d omega by dk, which we have calculated, and the group velocity is c divided by 1 plus a by omega square. So, this factor is going to be more than 1. So, the group velocity is going to be less than the speed of light. So, the modulations do not propagate faster than the speed of light in vacuum, and you cannot send signals at a usually the group velocity tells you the speed at which you can use the wave to send a signal. So, it turns out that you cannot send a signal at a speed faster than the speed of light in vacuum using X-rays by sending it through a medium. It cannot be done. The group velocity is less than the speed of light in vacuum. So, you cannot send signals faster than the speed c using this X-ray in a medium. Now, it is a fundamental postulate of physics which is very important for Einstein's theory of special relativity. The fundamental postulate is that no signal can propagate at a speed faster than the speed of light in vacuum. It is a fundamental postulate, and till date there has been no contradiction of this fundamental postulate. If there was a contradiction, then you would have to revise the whole of physics as it stands now. So, till date there is no evidence that you can actually send signal faster than the speed of light in vacuum, and this is consistent with that postulate because the phase velocity is more than c, but the group velocity, which is usually corresponds to the speed at which you can send signals. The group velocity usually tells us the speed at which you can send signals, and the group velocity is less than the speed of light in vacuum. So, let me end today's lecture over here, and we are going to go on to quite different topics from the next. We have finished interference, diffraction and superposition of waves. We are going to go on to quite different topics from the from the next lecture onwards.